Okay, last time I guess that we finished chapter 11, and that is the material required for our midterm. Yesterday I sent you an email with the schedule of the midterms for chemistry. The rest of the exams, I mean, they should be communicated with you through your instructors, everyone. We thought about sending the whole, table for everyone, but then that's a lot of confusion, though, because that's for business and engineering and medicine and everyone. So anyway, for the chemistry, the first one is Ragad Al-Ghamdi. Can we attend? Well, that's fine, yeah, Ragad. You can attend, of course, but why are you saying we? I mean, do you have somebody else with you? Yeah, Ragad. Anyways. No, she's new to the. I know that she's new, but she's saying, well, you should have asked. I mean, it is a hybrid mode, so you can attend if you want. There are some of your colleagues are here. Anyway, starting not this Thursday, because Thursday is a lab. Speaking of that, let's talk about the announcement since she asked. First of all, the lab is this Thursday, so don't come to the class because I will not be here. The lab is 100% online. There's no virtual. I mean, there's no personal or in person. The Zoom link is there on the Moodle. I think everybody have seen it. So it is different from the Zoom link for the class. Okay, it says that this is the Zoom link for the lab. The second thing is, since we finished chapter 11, the homework is there, but it will open, I think, sometimes either today. I forgot, but it is today till Saturday, as usual. And as usual, no excuses. If you miss that homework for any reason, please don't send me emails, and I'm not going to respond to that. March? I will change it, don't worry. But thank you for letting me know. I will make it on. Huh? Oh, no, I did not know. Well, I should guess what? When you learn how to make it, then you will see that it is very easy to move from one month to another. It's just a click. Anyways, we'll fix it. If you want to keep it till March, we can keep it. That's no problem. Why not? What is the benefit from that if it is kept till March? You have the exam. Yeah, Ragad, your personal questions, just leave it for yourself. I mean, you can ask me directly. I'm not here to solve things for, you, okay? Send me an email or come to my office for these kind of questions. Where can I find problems and all that? You can ask your colleagues. Look at the course syllabus, though. So we talked about the lab. We talked about the homework. We talked about the exam and the dates that are there. Okay? طيب. Anything else before we move on عشان not to be interrupted? No, of course not. Come on, يعني 2 chapters and you need a review class? If we have chapter 12 added, yes, we may, but no. With 10 and 11, though you can come and ask whenever you need. And okay, so chapter 12 in stoichiometry, and that is the defined as the kind of quantitative analysis that we do whenever we have a chemical reactions in terms of the quantities that we start with and how much product we can produce. In order to, as usual, for any new topic like this, we start up with some basics, and then we move into the real calculation, which is a chemical calculation. It doesn't mean that we're not doing something real, but we're going to do some bicycles and stuff like that. What are the objectives for this section is, First of all, we need to see how important it is to have a balanced chemical equation. That's why we taught you how to balance a chemical equation before, because without the chemical equation being balanced, that doing your calculation will be, off for sure. So you have to make sure how to use that one. And then we're gonna describe the quantities that used to interpret the equation. And how can you read a chemical equation? When you have, for example, H2 plus O2 produces H2O. We read it as 1 mole of H2 plus 1 mole of that to produce 1 mole of this. Or we can say 1 molecule of that react with 1 molecule. This is the way we can interpret it. And we will see all the types and how to do that. Then we're going to talk about the things that are conserved, and you know that the mass and the number of atoms is the only one which is conserved. The number of moles and other things, they are not necessarily to be conserved. And you start with 5 moles, you end up with 2 moles. That's normal because the mole of one thing is different from another mole of another thing in terms of the mass. So the quantities that are conserved in a chemical reaction are the mass and the number of atoms. How do you, this is the question and a picture as usual, we're not going to spend too much time on it, but how do you figure out how much starting material you need to make a finished product? How would you know what starting material you need to have in order to have a finished product? What is the only way to do that? Calculation of what? How are you going to do calculation? There's something missing still. What is the, how do you figure it out? By calculation? Is this, do you think this is a reasonable answer? He's asking you how to calculate the how much product you're gonna have. Yes, you need a chemical equation or equation to relate the quantities of the reactant with the product. Then you can do calculations, right? So that's what you need. How are we going to use the equation? This is again not a bicycle this time, but a tricycle. If you are making working for a factory that making tricycles, it's like making ammonia, but in this case, making tricycles. This is what you need. These are the parts that you need in terms of the quantities needed. So you need 1 frame, you need 1 seat, you need 3 wheels, you need 1 handling bar, and you need 1 pedal like this. Okay, so we can convert this equation into symbols in order to make it easy. But if you were working for that company and somebody asked you, we need to produce 640 tricycles per week, then you need to know how many of those you need, right? At least you know 640 seats, for example, right? So that's the meaning of the chemical calculations. So these are the things that we need. This is the formula for the product. The product, which is the tricycle, is made from 1 frame, just this one. So it's made from 1 frame, 1 seat, 3 wheels, 1 handling bar, and 2 pedals, as a matter of fact, because he counted this as 2. All right. So once you do that, then you can write an equation like this. This is an equation for the tricycle, but you can write something similar for any chemical reaction. That's what we learned in chapter 11, is how to write chemical equations for different types of chemical reactions and how to balance it. The most important thing before you do any calculation is to make sure that your equation is balanced. If your equation is balanced, then of course you can do your calculation. Here's the question that I asked at the beginning, which is if you have, if you work 5 days per week and you need to produce 640 tricycles, how many wheels you need? The easiest way is to say 640 times 3, right? That's not the right way to do it, because this is the old, what you learn in high school is just multiplied. And some people, they might say, use what they call cross multiplication. Say, for example, 1 tricycle will need 3 wheels. So if I have 640, then how many wheels I need? This is the one that you need to forget using this anymore. We're going to use convergent factors. And the reason for this is that you don't make mistakes and you don't miss the units for the product. Okay, that's the idea behind this. I will show you that. Okay, so This is a 640 that is made from these parts. This is the formula for the product. Instead of saying tricycles, we can call it FSWHP2, like H2O, for example. Okay, so we need to see how many wheels. You see, these are the conversion factor. Where I got these conversion factor from? These are getting from the chemical equation, because if I take you back to the equation that we started up with, this one, here what we go, we have 3 moles, three wheels in order to produce one of those. So we can have this divided by that if we were to calculate the number of tricycles, or we can use the number of tricycles divided by 3 wheels if we want to calculate the wheels. So that will lead us into these two conversion factors. Again, extracting a conversion factor from a chemical equation is a key thing in these calculations, because we're not going to give you that conversion factor. That is your responsibility. But it is very easy. We'll see that when we have a real chemical equation, that just look for the coefficient in front of the whatever you are trying to calculate, and you relate them to each other. Okay, you will see that when we now learn how to interpret the chemical, how we read it. Meaning, when we say how to interpret a chemical equation, means how you can read it in terms of mole or volume or mass or any other thing. But anyways, for this tricycle, which one do you think we should use if we want to calculate the number of wheels? If the given quantity is the tricycles, which one, the green or the red? The green. طيب, what do we have? 600 tricycles. يا خلينا نضربها ب 640. ايش الرمز تبعها هذه؟ اللي هي هاي، صح؟ FSW3HP2، صح؟ شو هيك بدك يا يارا؟ شو الجواب راح يطلع؟ 640 over 3. بغض النظر عن النمبر, what is the unit for that is going to be? It's going to be FSW3HP2 square. So that's why this is not the right conversion factor to use. Remember that if you want to check which conversion factor you need to use, you look for the given quantity, the quantity that you have, and make sure that it has the same thing in the denominator here, so you can cancel the units. So this multiplied by 640, whatever, F blah, 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 this will cancel with that, and then you end up with wheels. Okay, that's why we don't want to use that cross multiplication, because that's where you make the mistakes. If you ever make a mistake in the cross multiplication, you will not find out whether you made a mistake or not. But here, because you plug in the units and the conversion factor, if you make such a mistake like what Yara did, which is, thank you very much for making the mistake, that's the way you find out if you have a problem. Okay, so you cancel the units with each other, and that is 1920 wheels. If you want to evaluate your answer, how you do that? Go ahead. حط رقم وين؟ مش فاهم هذا. شو نسوي فيه هذا؟ ها؟ We do rounding to something that is easy to calculate. يعني we assume this is 600. 600 times 3, it is known that is going to be 1800. So your answer should be close to the 1800. If your answer is far away from 2, you know, but 1920 is a close answer. You guys forget. That's what I thought. That's fine. Always, when you want to evaluate your answer, you make it by rounding into something that is very close to. When somebody say, for example, 3.5 times 7. You know that 3 times 7 is 21, right? That's easy. But 3.5, some of you, if not most of you, will go and use a calculator for that. Okay, so what you do is you assume that it is 3 times 7. So my answer should be around 21. It's not going to be 82. That's what we mean by evaluating your answer. You multiply 7 by 3, that is 21. When you do it with your calculator, you're going to get 24.5, and then you realize that at that time that Yeah, this is very close because when I round it to 3, whatever answer I'm get is little bit lower than the actual one. 21 is very close to 24.5. Okay, now we're done with bicycles, tricycles. This was just an example to get your appetite into the what we need to do. We need to deal with chemical equation. Balanced chemical equation is the basis for any calculation. So a chemical equation is needed, and it has to be balanced. And this is one of the mistakes that many of the students fall in whenever we have exams in chapter 12 or homeworks, that we put sometimes the equation without being balanced. Or even sometimes we don't give you the equation. We just say this material reacts with that material to produce hydrogen, reacts with nitrogen to produce ammonia. It is your job to write the chemical equation, first of all, and you learn how to do that, right? And also, it is your job to balance it. Make sure that it is balanced in terms of the atoms. Once you do that, then you start what we're going to teach you how to do that today, which is using that chemical equation that is balanced is the basis for how to calculate how much reactant is needed and how much product you can produce. This is going to be our job in this whole chapter, is to do this. Find how much material we need and how much material we produce. Either one of them is going to be missing. But if you know one of them, like if you act X plus Y to produce W, okay, and we have here 2, 3, and 1. Oh, well, we don't have to say 1. Okay, equation like this, assuming that it is balanced. Well, here we don't know what W is, but anyways, it is assumed that it is balanced. Then if we provide you with any of them, any of those 3, you should be able to calculate the other 2, because now you have a relationship. The chemical equation is showing you the relationship between the reactants with themselves and each one reactant with the product, and the product with the reactants. For example, for each 1 W, you need 2X. This is a relationship, right? For each 1 W, you need 3Y. For each 2X, you need 3Y to react to it. And for each 3Y, you need 2X to react to it. That's the meaning of a chemical equation from a stoichiometric point of view. If you understand any chemical equation this way, then if I say, if you have 9 grams of this, how many moles of that you can produce? That should be, now you're going to use your own previous knowledge, which is how to convert mass into volume and how to convert mass into moles and how to do all these kinds of conversion. Then you need to change 9 grams into moles first. Okay, once you do that, then you have 2 moles to 1 mole. That's a conversion factor, and you can do it. Well, we're not discussing that yet. I'm just giving a general example. Let's see that, how you can, if you know the quantity of one substance or the reactants or the reaction, then you can calculate the rest. That is something that I was telling you. This kind of calculation, that's what we call stoichiometric analysis, or the calculation of the quantities in a chemical reaction. And this is very important. You remember that airbag that I was telling you about the other day? If you were an engineer working in there or whatever, you graduated as a medicinal doctor, but you couldn't find a job. They put you in a car manufacturing plant, okay? And you were to calculate how much sodium azide we should put if the airbag that we need is 10 liters. Then if you don't know how to do stoichiometric analysis, that will be impossible for you. Okay, so it is like a bookkeeping and all that. I don't, let's go and see chemical equation, what quantities we can interpret. How can we read a chemical equation? We can read it by many ways. This is the example that you're going to see too many times, which is the formation of ammonia gas from nitrogen gas and hydrogen gas. In order to have this equation balanced, we need 1 mole of, or N2, I'm not going to say 1 mole yet, 3 H2O, H2, that will produce 2 NH3. Okay, this is a balanced equation. Look, take a look at it. Is it balanced? Yeah, Muhammad? It is? It is balanced. 2 nitrogens and 6 hydrogen. Okay, and we have on the other side 2 nitrogen, 6 hydrogen. So it is balanced. That is the equation that we will use in order to do the calculation for either how much nitrogen, how much ammonia we can produce, or it is not in the model. I thought I did. Anyways, it's just for now, and I'll do it after that. The lecture for today is not in the model? Okay, because the other section we did not finish chapter 11, so I thought that, yeah, they were a little bit slow. Right, anyways, if we have nitrogen reacting with hydrogen that will produce ammonia, then this is a balanced equation. If we give you one product, you can read it, the whole equation. Okay, relative amounts is the one which is relating those, how to interpret it. That's what I want to do, is that you can interpret or read a chemical equation in many different ways. For example, in terms of atoms. Can you read it in terms of atoms? Yes, you can. Let me just take you back to that. How many atoms of nitrogen we have here? 2. So we can say 2 atoms of nitrogen reacting with 6 atoms of that to produce the same number of atoms. Why the same number of atoms? Because the number of atoms is conserved. Okay, so in terms of atoms, we can read it in terms of molecules. We can do that in terms of moles. We can do that in terms of mass. And also we can do that in terms of volume. And you know that all of these molecules and atoms and moles, these are counts, right? The mass is the mass. So we have 3 things. We have the count, the mass, and the volume. Remember when we did the beaches and apples, and some of you were laughing at that time. Oh, well, we are here to learn about how to count, apples and oranges. That was the purpose. And the sand that was in the beach and all this. This is to be used at this time here. We have 3 ways of measuring things, either by count or mass and volume. You know how to go from one to another. So you can read any equation by any of those. All right. So if you want to do that, then let's do that with number of atoms. As I said, it is 2 atoms of nitrogen based on the equation. 6 atoms of hydrogen, that will produce 2 atoms of nitrogen, 6 of hydrogen. If you want to read it in terms of molecules, you can do that, which is 1 mole of nitrogen with 3 moles of that to produce 2 moles of that. Or if you want really to get the actual number of molecules, you know that each 1 mole of any material will contain Avogadro's number of representative particles, which are, in this case, the molecules. So it is 1 times Avogadro's number of molecules of nitrogen times 3 times Avogadro's number of hydrogen. This should be hydrogen. And that will produce Avogadro's number of ammonia times 2. Where we get these 1 and 3 and 2, these are the coefficients in the formula, in the balanced chemical equation. Why we use Avogadro's number? We can use it, or we can use 1 molecule. It doesn't matter. The relative is the same. يعني the relationship between number of molecules of nitrogen and number of molecules of hydrogen is still 1 to 3. Whether you multiply it by Avogadro's number or you don't, it's going to be the same ratio. All right. So you can do it in terms of moles as well. You can read the chemical equation in terms of moles. You can say 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. I personally, or you will see that this is the best one to use, to read it this way. And then you know that the mole is what? It is a central unit that you can go from a number of particles. How you do that? How you go between the moles and number of particles? Using which number or which convergent factor? Yeah. What is the number of particles? Okay, so Avogadro's number, that's what you need to say. Okay, so you remember that shape that we had in so if I want to do with mass, what you use here? What we call it, mass over mole. You are using the wrong terminologies today. It is called the molar mass. Okay, it is the molar mass, the relationship between the molar mass. What about if I have a volume over here? What should I use in order to go back and forth? molecular number. شو الموليكولر نمبر هذا؟ أول مرة أسمع فيه. Do you know what molecular number is? Volume. I'm talking about volume, guys. First of all, there's a requirement over here. That is, yeah, thank you very much, غايدة. كويس إن أسعفتيهم. It is the molar volume, and the molar volume is the volume of 1 mole of a gas under STP, and that is 22.4 liters. That's the one which we use in here. I thought that you guys already remember this shape and you're going to be using it. If you don't know this one, by the way, what we're doing here is wasting of time, to be honest with you. You're not going to be able to understand this unless you know that one, because every time we're going to refer to it. So that's what we keep saying. Before you move on into another new topic, you have to make sure that you understand the previous one. Okay? That's why they are in chapter 10. We talked about the quantities and how to do all the changes. In chapter 11, we showed you how to write a chemical equation and has to be balanced. And now we're going to use the knowledge from both chapters in order to do stoichiometric calculations. So if you don't know this kind of conversion, that will be difficult to deal with. Anyways, طيب, you can do it by mass. Yes, you can. You have to convert the masses of that. If we have 1 mole of nitrogen gas, that is 14 times 2. Where's the 14 is coming from? That is the atomic mass of nitrogen. But since we have it in the molecular form, so that is N2, that's 28 grams. And we have 3 moles of nitrogen times the 2 grams of each for the hydrogen, and 2 times 17. At the end of the day, they have to be the same, ولا لا? They have to be the same because the mass is conserved. So the total here is 34 and 34, and that's why it can be read by the way. You can read it by volume under temperature and pressure conditions. And that is, again, the volume of 1 mole of a gas under that kind of condition is equal to 22.4 liters. So since we have 1 mole of nitrogen, so that is 22.4 liters of nitrogen. Since we have that react with 3 moles of ammonia, of hydrogen, so this means that we have 3 times 22.4 liters of hydrogen, because it's 3 moles. That will produce 2 moles times 22.4 liters of ammonia, because that is the volume of any gas under STP. All right. Now, if you look at the total liters here and there, you're going to find that it is not conserved, which is normal. That's fine. The liters doesn't have to be conserved. And the moles also doesn't have to be conserved. If you look, this is the only one which is conserved. The mass and what else? The moles? No, the moles, look, we have a total of 4 in here and we have 2 on this side. So that's a total of 4 and we have 2. So it's not conserved. And the atoms is the number of molecules is not. If you go to the atoms, where's that atoms? Yeah, here. Number of atoms is conserved. So the only one which is conserved is the atoms and the mass. Volume, molecule, moles, they are not necessarily to be. Why they're saying not necessarily? Because it happens sometimes that you see that the number of moles are the same. So they don't want to say never. Then you're going to say why it is conserved now. It is not conserved, but not necessarily conserved. That's what we are going to see here. This is an example, a different example. If we have an equation like this, which is the reaction of hydrogen sulfide with oxygen to produce sulfur dioxide and water molecule. This is a balanced chemical equation. He wants you to interpret this equation in terms of number of representative particles and moles. Let's do the moles first. How you can read this equation in terms of moles? I didn't tell you to speak, right? There's some other people here. They want to answer the question. You raise your hand, and if I tell you, then you speak. Yes, Ciara. 2 moles of what? Okay. Not and. See? That will produce. Because if you continue saying and, this means if somebody is not looking here and listening to what you're saying, you tell him 2 moles of H2S, he will write it, and 3 moles of oxygen, he will write it, and this, then these are reactants. So you have to read this arrow here that this will produce 2 moles of sulfur dioxide and 2 moles of water. Okay, so that is in terms of number of moles. If you want to do that in terms of number of representative particles, the particles here are what? Representative particles. Are they ions, are they atoms, or are they molecules? Atoms. So we have, where is the atoms? Where do you see the atoms here? Representative particles. How the H2S is represented here? Is it by number of atoms or molecules? It is molecules. Come on, you guys keep making, you use the atoms when you're dealing with element. And you use molecules whenever you're dealing with compounds. So these are compounds, none of them is an element. If you want to do atoms, a number of atoms, yes, you can by making these 2 hydrogen and that, you can do that. But here the question is about representative particle, how the H2S is represented in the equation. It is by the number of molecules. So this will be what? Either you can say 2 molecules of H2S react with 3 molecules of oxygen to produce 2 molecules of that and 2 molecules of water. You can do that. But also you can do 2 times Avogadro's number of molecules of this, because that's 2 moles. And 3 times Avogadro's number. You're adding Avogadro's number to them, so it's not going to make a difference. You know that if you multiply, if you have an equal sign, and you multiply both sides by a factor, nothing is going to change, right? So that's why multiplying by that is not going to. No, I did not say that. Or what I said is 2 times 6.02 times 10 to the 23 molecules. So where is the number of moles and molecules are the same? I don't know where you got that from. No. I said you can use the representative particle as molecules without multiplying by that. Don't you? I mean, these are 2 moles, right? But isn't it 2 molecules or لا? I can use 2 molecules. فمش معنى ذلك your statement is wrong, although in terms of number it might say the same thing. You're saying that the number of moles and molecules are the same. And I'm telling you in terms of concept, no. But in terms of reading the equation, yes, you can read it as 2 molecules. انتوا تنتبهوش لما بوريكم شغلات. وين راحت؟ هاني شو سويت انا؟ What did I use here? Nitrogen. 1 to 3 to 2 molecules. But if you want to get the actual number of molecules, you multiply it by conversion factor. طيب يا شو اسمك انت؟ هنا مش هيك؟ 2 ضرب 3 يساوي، او لا بلاش، 2 زائد 3 يساوي 5. اوكي؟ طيب خلينا نضرب هاي في 2 وهاي في 2 وهاي في 2. شو بصير؟ تغير شيء في المعادلة؟ That's what exactly we're doing here. We're multiplying by the Avogadro's number. That's not going to change the number of molecules. It is the same thing. But this is an actual molecules. طيب, masses of the reactants and the products. When you do that, then you have to convert all the moles into molar masses of the atoms. يعني هنا بدك تقول إنه either you calculate the molar mass of this and you multiply by 2, or you can do 2 times hydrogen, that is 4 from the hydrogen, 2 from the sulfur, that is 2 times the atomic mass of sulfur, and so on. I'm not going to do that, but I'm going to show it to you. So the coefficient in the balanced equation gives the relative number of representative particles. هذول النمبرز الموجودين لما نقول N2 plus 3H2 to produce 2 moles of ammonia, these coefficients, which is the 1 that's not written here, the 3 and the 2, these are number of representative particles and moles of reactants and products. Okay, they can be used as representative particles or they can be used as number of moles. But if you want to really get the number of representative particles exactly, again, these are the ratio that we're talking about. If you want to get the actual one, yes, you need to multiply them by the Avogadro's number. Okay, so that is what you're trying to do here is to explain the concept that we will use in order to answer the question. Okay, so that is either we can say 2 molecules of this with 3 molecules of that times that. We can do it with moles, but if you want to multiply here, Hannah, by Avogadro's number here, by Avogadro's number there, by Avogadro's number here, by this, it's not going to make a difference. So, either you can use the molecules as the coefficients, or you can use the coefficient multiplied by the Avogadro's number is the same. The moles is the coefficients. There's no doubt about it. Right. This is how to do the mass. As I said, you calculate the molar mass of H2S, and we have 2 moles of that. The molar mass of O2, which is 32, and we have whatever number of moles of that. If you add them up, they will be like that. 2 moles times 34 over that. Where the 34 is coming from, that is the molar mass of H2S. Why we multiply it by 2? Because we have 2 moles as per the equation. The same thing about the oxygen, 3 moles times 32. Then you are sure 100% that whatever answer you get here, it has to be the same as the other one. Why? Because the mass is conserved. The mass should be the same. Nothing is going to change. If you do that, then you're going to get 164 grams in the reactants. You end up with 164 in the product. Regardless of what you do, you end up with the same. You remember when I showed you this concept of conservation of mass? There was 2 glass bottles. One of them is orange and the other one is yellow. We mixed them together on the scale, and the scale did not change. مذكرين هذا chemistry 1 ولا واحد فيكم مذكر؟ يعني 1 من 10. Okay, so the mass is conserved in this case. طيب. This table here summarizes the whole thing that you want to know, which is the same reaction, that is nitrogen. I'm looking at this all. What is all? I forgot. N2 plus 2H2, that is wrong to start with. That should be 3, isn't it? Okay, to produce 2 moles of ammonia. You can do it like that if you wish. That's by drawing the molecules. You can do it by atoms and make it 2 atoms of nitrogen, 6 atoms of hydrogen, that will produce the same. So this is conserved. That's why it is marked with red. You can do it as molecules, but you could multiply it by 10. You see, between here and there, whether you multiply by 10, multiply by Avogadro's number, it's not going to make any difference. The ratio is the same in terms of the representative particles. So all of these are representative particles, regardless whether you use the coefficient as it is, multiplied by a factor, or multiplied by Avogadro's number, is going to remain the same. The moles are the coefficient themselves. You cannot multiply it by anything else. So it is 1 mole of nitrogen with 3 moles of hydrogen. And I'm telling you, this is the one that you need to keep practicing so you can use every time you want to do a calculation. Because at the end of the day, you will use a conversion factor that are extracted from a chemical equation. Okay, so but then this is the mass. The masses should be the same. If you do the molar volume, it is 1 mole of nitrogen, so that's 22.4 liters. It is 3 times 22.4 liters of oxygen is needed, and you produce 48 liters of that because that is 2 moles. As you can see, this is not conserved, and that is okay. The volume is not conserved. The moles are not conserved. The representative particles are not conserved. The only one which are conserved is the atoms and the grams, the mass. Okay, so this table should have summarized the whole thing what we talk. But this is what you need to know. But I'm telling you that if you can read any equation with the moles, you should have no problem. يعني, what is the conversion factor between hydrogen and nitrogen in this case? It is either 3 moles of hydrogen divided by 1 mole of nitrogen, or 1 mole of nitrogen divided by 3 moles of hydrogen. How will you decide which one to use? It is the given amount, the one you have in your hand. If somebody says, telling you, if I have 2 moles of nitrogen, how many moles of hydrogens is needed? Of course, you can do, because it's 1 to 3, you can say 6 moles. But this is not the way to do it. You have 2 moles of N2. This is what you're given amount. You need to multiply by a conversion factor. What you need to have here, it should say moles of nitrogen. لازم تكون moles of nitrogen. What is the moles of nitrogen here? It is 1. And here it says moles of H2, which is 3. That's the way you find the conversion factor, okay, from a chemical equation. If you want to do the conversion factor between hydrogen and ammonia, it is 3/2 or 2/3. It depends. If I ask you how many liters of hydrogen is needed to produce 2 moles of ammonia, for example. So what you have in your hand is 2 moles of ammonia. You take that and you convert it into moles of hydrogen using this kind of relationship. Then after that, you look for the quantity that the question is asking you about, which is how many liters. Then you have to use the molar mass kind of, which is 22 per liter. Okay? Masses are not conserved, the other one are not conserved. Okay, interpret the following equation in terms of volume of gases at STP. That is the easiest one, right? Since they are all gases, or the reactants and the product all of them are gases. So we can use the molar volume in this case under STP. So that is 2 times 22.4 liters of hydrogen reacts with the same volume of nitrogen oxide to produce 22.4 liters of nitrogen gas and 2 times 22.4 liters of water vapor. Okay, this is the way you read it in terms of the molar volume. بس good timing. يعني المشكلة في the other section that I have to do the other section. Any questions? So starting next section, if you don't review this one and understand it, راح تيجي المرة الجاية وتكون قاعد بدون فائدة بصراحة. Yes. لأنه if you don't understand كيف بدك تفهم المرة الجاية؟ لما نبدأ في الكالكوليشن, if you forget all what we learned today. مش فاهم. فهم كويس. هذا الفهم بده يظل موجود للمرة الجاية وforever. مش تيجي المرة الجاية ناسي. لما تكون نسيت كل اللي قلناه ونيجي المرة الجاية نروح على section 2 which is chemical calculations. راح نسوي اللي قلت لكم اياه هلا. اقول لك how many moles of this can produce moles of that. If you forget what we learned today, or if you don't review it at home, and before you come into the class you should look at that and review it again, يعني بتصير زيك زي واحد قاعد هنا كان أول مرة اسمع صيني بحكي أنا ولا شيء ثاني. And that is mainly the problem is with most of you. بتفكروا إنه coming to the class إنه أنا بدي يعني أجيب المعلومات وأفتح إشي في راسك هيك وأصب لك إياه. That's not going to happen unless you know what we are talking about. شفت الحين لما رجعنا نحكي عن المولر mass والمولر volume how to convert between moles. Most of you don't know that. Forgot it. وهو في chapter 10. عشان هيك it's an accumulative knowledge. 100 مرة صرنا قايلين هالكلام. Okay, can you just please write your names? We don't have the lectures for chapter 12. خلاص يا أخي we don't have it. إن شاء الله هم نحط لك إياه. فضحت الدنيا.